Yeah.
Okay, welcome people of the pre-seminar. We are very happy to have as a visitor Deeponjit Bose, and he is going to tell us about pseudo-differential operators and the Wodzicki residue. Please.
I just joined as a doctoral fellow in mathematical physics under Professor Andres Sitas in Jagiellonian University. It's only 2 months, so I'm trying my best to give the talk. So let's start. So my plan of the talk will be to revisit the concept of linear differential operators and to extend the concepts of them to pseudo-differential operators, and I will show that they form an algebra, and I will then define a unique trace on the algebra, which is basically the Wodzicki residue, and I will show its connections to the spectral triples. How Wodzicki residue is, it's get connected to spectral triples. What does it contribute? Because after all, this is a non-commutative geometry seminar. So let's start. So in the first slide, I have consider in one dimension. For simplicity, consider a linear differential operator ddx, which is acting on some Schwartz function f, such that df dx also is a Schwartz function we all know, and the Fourier transform of the Schwartz, Fourier transform of df dx is given in this expression. Okay. Yeah, Schwartz class function is, because I'm doing the Fourier transform. So, for all transform, for all functions, Fourier transform may not exist. So that's why I'm assuming it to be Schwartz function, such that it's asymptotically, it will, rapidly decay faster. It will decay faster than any polynomial of x. So, yeah. 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 Okay. Sure. Yeah. So that's why I specified the Schwartz function. So in my notation, this Fourier transform of df dx is giving me, after evaluating the integral, it's giving me I xi and times the Fourier transform of fx. So this is basically the Fourier transform of fx. This, and this is my definition of Fourier transform of fx. I'm taking this notation, and then we can rewrite this df dx as the inverse Fourier transform of the Fourier transform of df dx, which is trivial. But when I write in this form, then it's kind of a representation of the linear differential operator in the Fourier space. So you can see that for every ddx, we are getting an I xi as a multiplier or a symbol. That actually we call this sigma xi as a symbol here. And this fx is basically mapped to the Fourier transform f in the xi space. So now we can, now you can ask me that, okay, it's for ddx we are getting like this. So what will be in the case of a more general linear differential operator? For example, gx ddx in one dimension, of course, of order 1 I'm taking. So we can multiply this. Actually, we can plug gx on both sides, and we can get, obviously it's trivial that gx ddx can also be written down in this Fourier transform way. It's kind of representation of the linear differential operator in the Fourier space in terms of the symbol. So we call this sigma xi as a symbol. So this sigma xi actually encodes all the information about the linear differential operator. You see, because for ddx we are getting I xi, and for gx ddx we are getting I gx xi, and we can generalize this to any order of and in any dimension also. We can generalize this formulation in any order. So we can generalize any such linear differential operator on Rd, like with this expression where P is a linear differential operator of order any order, and it's acting on this acting on the SRD. This is a Schwartz function of Rd. So, and this will be given like 1 by 2 pi d integration over whole Rd and d xi, and this sigma p is a symbol. For every p we are getting a sigma p x comma xi, right? So for simplicity, I'm just noting this down that in the case of a simple differential operator, we are we can observe that every such linear differential operator I del x mu whole to the power n, this is getting mapped to sigma p xi mu n, right? For every del x, we are getting I xi. So any function of del x will be just mapped to any function of f xi. Of course, if it's linear differential operator. So this formula, I mean, this expression is very useful. We will use this expression to define the action of pseudo-differential operators also. We will generalize this expression in terms of in the case of pseudo-differential operators. So, and also I want to state a remark that this construction can also be generalized to manifolds through charts and classes, because I'm talking about RD, so it can be generalized. So, okay. So now what is a pseudo-differential operator? What do I mean by that? So pseudo-differential operator is basically a differential operator of any order. Maybe it can be a real number. For example, I mean, it can be ddx whole to the power alpha, where alpha can be any real number. I mean, it's like that. And so that's why it's, I mean, it will act linearly, but it's not, I mean, for example, ddx whole to the power alpha acting on f cannot be, I mean, written down like the usual notion of differentiation from the first principle that we have. So we will define this pseudo differential operator in terms of algebra and the expression that we did in the Fourier space in the case of linear differential operators. So we say that now how we define. So we say that in the case of linear differential operator, for every p we are getting a sigma p x comma xi, a symbol, and here also we will get the same thing, but how we will define the order of the differential operator. So we'll define like this, that we say that sigma p is the symbol of p, is a total symbol such that this it satisfied this expression. Okay, so for any I mean dx and d xi acting on this sigma p, where dx is basically this, because I am plugging minus I into the del x, because for every I del x we are getting xi, right? So that's why for simplicity I have inserted minus I into the operator del x. So I have redefined this. I mean d alpha x is basically minus I whole to the power summation of all alpha, and this is the multiplication of the. I mean, this is the generalized differential order differential operator in any dimensions. So yeah. Yeah, because we are defining a symbol of because see, I mean, this sigma is actually we are defining to be smooth in x, but its order is in terms of xi. So yeah, so you were saying, yeah, because in the previous slide, if you notice that this this thing del x, I mean mu whole to the power n is mapped to xi mu whole to the power n. So the order of the differential operator is transferred to the order of xi only, so not x. So that's why we have defined like this. So it's xi m minus beta, not alpha. But we have differentiated with respect to x so that it's bounded actually. It's one of the definitions of so this dx comes from one of the definitions of Schwartz function actually. So so this is our definition of what do I mean of p, I mean pseudo-differential operator of order m, and its corresponding symbol sigma p. Okay, now I proceed. Now a classical pseudo-differential operator. I mean, what do I mean by classical differential operator? For every p, we're getting a symbol sigma p x comma xi, and now this total symbol will satisfy the previous condition that I have shown in the previous slide. But it can also be splitted down into some homogeneous terms. But all these terms are basically homogeneous in order m in xi, of course. So this is actually homogeneous in xi of order m. This sigma p m minus 1 is basically homogeneous in xi in order m minus 1 like this. So it will be homogeneous in k, of course, in xi. So this now if I say that okay, the pseudo-differential operator is of order m, that means we will get a symbol that can be split into the homogeneous symbol starting from the leading order. And this is, if I say m, then the expression should start from m. This is the leading top order. So the top order, I'm calling it as the principal symbol. So homogeneous means, I mean, I have not written it, but you all know that this satisfies sigma m x comma lambda xi equals to lambda m sigma x comma xi for all lambda greater than 0. So, yeah. I mean, for the usual differential operator, it's a very good point. It would end from m to 0. It will, I mean, usual differential operator, what would be? It would be some a alpha x, I mean, a m x ddx whole to the power m, and m is going from m, I mean, sorry, you can have j as summation index, and j is going from m to 0. So in the usual linear differential operator case, the summation will truncate to 0. It will go from m to sigma 0, which is of order 0. But in classical pseudo differential operators, we can have two things. One is m is a real number, and it will go on, I mean, up to infinity. But you can say, but the notion of convergence is an issue. That's why I've given an asymptotically equals symbol. Yeah, this is that asymptotically equals symbol. So which I mean that this I mean the left hand side minus the right hand side is not actually 0, which is actually mean that the left hand side minus right hand side will give me a symbol of order minus infinity. What do I mean by that? A symbol of order minus infinity corresponds to a pseudo differential operator of order minus infinity. That is actually a kind of smoothing operator. For example, a smoothing operator, which is a pseudo differential operator of order minus infinity, will act on any function and give me a smooth function. So if it's a continuous function, then the smoothing operator psi_d minus infinity will act on, suppose, g, and it will give me an f that is a smooth function. So by this I mean that actually. So any continuous function, I will get a C infinity function from CRD to C infinity RD. So by this I mean this is asymptotical equals to, not exactly, because there is a notion of convergence there. So okay. So now I will discuss the algebra of pseudo differential operators. So by far I have introduced how to write the symbols and what does it mean. And now I want to define how to compose two symbols, right? Because for the algebra we need composition. So that is the most important part. So, now for that, yeah, say take P, which is a pseudo differential operator of order m, and Q, which is a pseudo differential operator of order n, and then we can say that PQ is a pseudo differential operator of order m plus n from that symbol expansion, since all of the terms are homogeneous. So, so this composition of symbols can be derived. It's like this. So for the symbol of PQ will be asymptotically equals to this summation 1 by alpha factorial and derivative of sigma p with respect to xi and derivative of sigma q with respect to dx. Dx contains this minus I plugged. Okay, so that's why these two are different expressions. This del xi will not contain I, but this dx will contain I, as I have introduced my notation in the previous slide. So now, and this is the total composition of the total symbols. Now you can ask me that, okay, now this is the of course I mean infinite sum, but we have a good news that for each homogeneous components of sigma pq, we can have this expression. So this sigma pq can also be split into a series of homogeneous terms, and the kth homogeneous term of pq. So this will be a finite sum actually. So this is a constraint ij mod alpha. Mod alpha is basically the sum of alphas from alpha 1 plus alpha 2 up to alpha d. So where d is the dimension, I mean rd, we are talking about rd. So basically, so and this is the constraint that I plus j plus mod alpha plus k equals to m plus n. So this is a finite sum. So I want to portray the message that even if it seems like it's an infinite sum, but for each homogeneous terms we are getting a finite sum. So this is the good news actually. And for principal symbol, it's very trivial. You just multiply the two leading order symbols together, and you will get the leading order term of the PQ, which is m plus n. Okay, so so we can see actually this. So we can see by expressions, and it can be deduced mathematically also mathematically rigorous in a rigorous way, that this algebra of linear differential operators form a subalgebra. It's a subspace of the algebra of the pseudo differential operators quotiented by the smoothing operator. Remember I told about the smoothing operator that actually it acts on any continuous function and will give me a C infinity function. So when this Pseudo infinity contains all orders. I have taken the union of all the pseudo differential operators of all orders. So Pseudo infinity basically is the largest space of all pseudo differential operators of all orders and quotiented by this ideal, algebraic ideal. This forms actually, I can check, actually it forms algebraic ideal that, so this Pseudo infinity is a smoothing operator. So this algebra forms, this forms a bigger space. So kind of, yeah, because actually, if we do not take, it's actually a kind of a homomorphism, you can see, from Pseudo M, because if you see the sigma expression, it's starting from M to infinity. So when sigma M, so there is no sigma M plus 1 term. So for every M, we are having sigma M plus 1, sigma M plus 2, this is 0, right? So this forming an ideal. So so when sigma M acting on some pseudo differential operator of order M minus 1, it is giving me 0. So sigma M acting on some lower order pseudo differential operators, it will give me 0. So this forms a non-trivial ideal. So we have to quotient out when we take the all union. So so that's why. So this is by far the definitions of the this pseudo differential operators and their algebra. So algebra of linear differential operators from sub algebra actually of this algebra. And this, and we can also, I've told you from the beginning that actually this classical CDO can give meaning to operators like ddx whole to the power alpha, where alpha can be any real number. And for example, the most important thing, the inverse Laplacian operators is also a classical CDO, inverse Laplacian operators. So yeah, I think so. Yeah. Now here I'm discussing the general thing, but when you have some Hilbert space and this thing, so you have to search for John this thing. Yeah, these have. I've seen some formulations also. They have some subdomains where these things are self-adjoint and we act on, and this forms the subspace of the pseudo-differential operator algebra. Yeah. So okay, now the main part. This is the trace on the. Now I've so far defined the algebra of the side classical pseudo-differential operators. Now we'll define a unique trace according to the theorem of Wodzicki. So take a compact closed manifold of Riemannian manifold, of course, of dimension greater than 2. Then we can actually, and we have the algebra, the algebra of pseudo-differential operators like this, right? And then we have this is the algebra, and we define a linear map WRES. This stands for the Wodzicki residue. It's a linear map which takes every element of the pseudo-differential operator algebra to a complex number, and this given by an integral. So Wodzicki residue of P is defined like this. It's integral over the manifold M, and then 1 by 2 pi d comes due to the Fourier transform thing, and then it's integral over the sphere of d minus 1 dimension, and we take trace of these symbols, because now see I've also written. This is a more general statement. If the pseudo-differential operators acts on sections rather than on the C infinity RD, then we will have a matrix valued representation of sigma sigma x comma xi. So we are taking trace for that case, and we are integrating out. So I will get a number, a complex number basically. So this is this basically a linear map from psi naught to C. Now this is the main part. Thanks to Wodzicki, that he proved this. That he also showed this unique property of this, that for any P and Q, for any P and Q that belongs to a pseudo-differential operator, take any P and Q which is a pseudo-differential operator, and we calculate WRES-P and WRES-Q, and then if we calculate the WRES, the commutator of the Wodzicki residue of the commutator of P and Q. then we will get 0. And this is one of the property that is satisfied by the trace, right? So if we have the cyclic property of trace of any two trace class operators. So, but instead they are not trace class here, so that's why we are not calling it a trace, but it's some sort of exotic trace. So W race of commutator of P and Q is 0. So from that, we can predict that it's going to be some kind of trace. So more specifically, here is the theorem that if this manifold is connected, rather path connected, then Wodzicki residue is the unique trace that can be defined on this algebra of pseudodifferential operators. So up to some multiplication constant, multiplicative factor. So now, so this is my last slide, because I will show that how it is connected to the spectral triple after all. So if you consider a regular P-summable spectral triple, which is consisting of sister algebra and Dirac operator and this Hilbert space. So whereby P-summable, I mean that the trace of Dirac operator raised to the power minus of complex number S is less than infinity. For every real part of S is greater than P. So by P-summable, this is the thing. And again, thanks to Kohns and Moscovici, they have established this connection of this residue to spectral triple that. So if you have algebra, this will also form a classical video. If you have an algebra, this algebra, this A is the sister algebra here. And if you also, you can also construct an algebra consisting of algebra and the commutators of Dirac operator with the algebra and all the powers of the absolute value of Dirac operator. But K is K belongs to integer. So and then they have proved this that P and P mod, the P absolute value of minus S is actually a trace class operator for every P belongs to for every P belongs to this algebra A naught, which is a algebra of pseudo-differential operators in our case. So this is a trace class, and if this is a trace class, we can define a usual trace in this operator, which is taken over the Hilbert space here. So this now this extends to a meromorphic functions on C, which consists of only isolated singularities of a finite number of poles. So now we define the non-commutative residue. This integral cut is basically, we are defining our notation. It's a non-commutative residue of P, that is residue of the trace of which is the usual trace, because P D minus S is a trace class. So residue of this trace of P absolute value of D raised to the minus S at S equals to 0 point. So they have defined where S belongs to complex number, it's usual. And this P is called non-commutative residue, and it's very special that under certain conditions, this after computing the residue, this also satisfies the properties of trace, right? And since you know that what is going to the, what is coming the next point, because I have in the previous slide, I have told you that Wodzicki residue is only the unique trace up to some multiplicative factor that can be described on the algebra of pseudo-differential operators. So logically, this should also be proportional to the Wodzicki residue. And this is also true. They have also showed this. That for a canonical spectral triple of a Riemannian compact closed manifold, this non-commutative residue is also proportional to Wodzicki residue up to some multiplicative factor. This also matches with the Wodzicki's theorem that he proved. So uniqueness of the Wodzicki residue. So with this, I conclude my talk. So this is the aim of my message, that I want to portray that for every pseudo-differential operator algebra, this is, we can have a unique trace defined on that algebra, and that is Wodzicki residue. If you come via spectral triple also, that will also yield you the Wodzicki residue. And this have some geometric applications also. It's sometimes you can see, if you have some operators, Laplacian operators, or some I plus delta all to the power minus n by 2, then you can see that it gives basically the volume of the manifold in some cases. So it's very interesting things to study on. So thanks a lot for giving me the platform to portray my message and Also, I thanks Professor Andres Sitar. He also helped me a lot learning this. And thank you everyone for attending the talk and giving me the platform. Yeah, thank you. Yeah. Yeah. Yeah.
Nice talk. Are there some questions?
The trace will not be unique. Are there known examples where
Non-commutative
in the
case,
for spectral triples?
I have told that in the canonical spectral triple. So in the
Sure.
it's
In the canonical classical case,
it's unique.
people in general, they're an easy example. In zero, and it's different traces.
Different traces. I think one may. I don't know actually. I have to carry this computation. I don't know whether it will yield non-uniqueness in the case of non-commutative torus or not. I have to work it out actually.
If I may comment, yeah, and I will talk about it in my talk. I mean, non-commutative torus is one thing, conformally risky non-commutative torus is the second thing. SUQ2 is another thing, and I will give the SUQ2 example as well. Yeah.
More questions? Maybe from the online audience, if you have a question, simply go for it. I see that there's something in the chat. Okay. So it's not relevant. Okay, so this is fine. Okay, then let me just note, so since this is the last pre-seminar of this year, let me say that I'm quite happy that we had many interesting talks this year, and I hope we can keep this going also next year. Let's see. So let's thank our speaker here and all of the previous speakers for their great talks. Thank you. And now there's a short break until